Today we want to talk about enthalpy and phase changes. When we look at a heating curve like this, and it just shows substances moving from one state of matter to another, and enthalpy changes are always involved in the process. Now, as we go in an increasing temperature direction this way, we've got certain processes occurring. And as we go in the opposite direction, we have other processes occurring. So we can see by looking at this diagram that if we're talking about increasing the temperature, we've got 5 different stages or 5 different areas of this graph to look at. Now I'm going to erase those arrows that I just drew so it will be a little less confusing on this diagram. If we talk about going from A to B, with this being the coldest temperature down here, then we're looking at the solid being warmed up. So this first part here we would call warming the solid. When we warm that solid, then we're going to need to calculate the amount of heat involved. This is a classic Q equals MCAT equation. That we would need for this if we knew the mass of the substance, the specific heat, and how much the temperature changed. There is a temperature change in this case, which is our big indication that we do need the MCAT equation. Now look at the next area though, going from B to C. Going from B to C, you keep adding and adding and adding heat, but you're not increasing the temperature any. So what's happening at that point? Well, that's our point at which we're melting that solid. So we're in the melting phase change here. Now, there is no change in temperature here, no change in the temperature, so we can't use the MCAT equation. And I just noticed that I didn't put a delta up here. So there is a change in temperature on the first one, needing the MCAT equation, but this one there is no temperature change. So what do we use for this particular one? Well, we use something called, well, something I call the MAW equation, Q equals M for mass times delta H. And since we're melting, this is delta H of fusion, enthalpy of fusion that we're going to use here. Honestly, I didn't know that fusion was another term for melting until recently. I went 30 years of teaching chemistry and didn't realize that fusion was an older term for melting. So heat of fusion for melting there. Our next range up here, and I'm going to be moving back and forth on this diagram, our next range here going from C to D then, we've melted it, it's turned it into a liquid, and now going from C to D, we're going to be warming that liquid. Now, if we're warming the liquid, notice what's happening to the temperature. It's continuously going up. So what equation are we going to need for this one? Once again, yeah, we're going to need Q equals MCAT because now, again, we do have a temperature change. We do have that change in temperature. But now we hit this next plateau, and going from the liquid then, heating it continuously but not having it change in temperature, what's happening there? Well, that's where we're getting vaporization. So that vaporization then is our next phase change. And the vaporization, since it is a phase change, we're not going to be able to use our Q equals MCAT. Once again, we're going to need to use our Q equals MAW. Now, the difference is we don't want the heat of fusion this time. We want the heat of vaporization in this case. Usually abbreviated as delta H sub VAP, heat of vaporization. But again, it's because there is no temperature change at this point. And finally, our last range on this table as we go from E to F is where we're warming up the gas, and we're just continually heating the gas. So once again, we can see that temperature change And since we have that temperature change, we're back to Q equals MCAT again. Now, the challenge when we're trying to determine the amount of heat that's involved in a process is to determine how many of these stages are involved in that process. For instance, if all we're doing is warming the liquid, then all we're going to need is Q equals MCAT. But what if we're warming the liquid and then vaporizing it? Well, then we're going to need to use Q equals MCAT, and then we're going to need to use our our Q equals MAW, our heat of vaporization equation, so we can also calculate how much heat is involved in that vaporization process. We might be taking it from the solid state to the liquid state and just barely vaporizing it. That's going to involve another set of the different stages in that heating curve. And we can do it in the opposite direction. We can cool the gas. We can condense that gas down into a liquid. We can cool the liquid. We can freeze that liquid into a solid, and we can cool the solid. So we can go backwards on that curve as well. In those cases, we're going to be giving off the heat instead of absorbing it. So let's look then at the most complicated problem that I could come up with, and that's one that's going to use all 5 of our different stages in our heating curve. It says determine the amount of heat required to change the temperature of 15 grams of water. It should be water, not hydrogen peroxide, from ice at -5 degrees Celsius to steam at 122 degrees Celsius. So we're going all the way from ice below its freezing point to steam above its vaporization point. So we're at all 5 stages. So we're going to need to find the heat involved at each stage. Yeah, a little bit tedious. We have to be careful about our calculation. And once we get to the end and we've calculated all the values at each stage, then we're simply going to add them up in the end to get the total heat that was involved. So let's just start out. We've got that first stage where we're warming the solid, and it gave us all the values we need here for water. And I guess I ought to go up here so there's not any confusion and say, yeah, we need to get rid of that too. This is just water, not hydrogen peroxide. These are all values for water. So warming the solid, we already said we needed Q equals MCAT. And we're dealing with 15 grams of our substance all the way through. The specific heat of ice is 2 joules per gram degree Celsius. So be careful and not just jump and use the 4.18 joules per gram degree Celsius because that's only for liquid water. So 2 joules per gram degree Celsius. And we're going from 5 degrees up to its freezing point. Now here it's good that we know some information about water. We should know that the freezing point / melting point of water is 0 degrees Celsius. So we should know that. So once we know that we've got then a -5 up to 0, a 5-degree change, then that's going to give us the values we need to calculate, and we come up with 150 joules for this stage. So there's our first value. In the next one, we need to find what happens when we are melting the solid. So this is the melting phase. And remember, for melting, we just need Q equals MAW. And this is the heat of fusion for melting. And notice our heat of fusion is given to us in kilojoules per mole. So what are we going to have to do with that 15 grams of water? We're going to need to change it to moles first. So Q is equal to 15 grams divided by 18.02 grams per mole, the molar mass of water. That's going to give us moles. And our heat of fusion we saw was 6.0 kilojoules per mole, which is going to give us our next value of 5 kilojoules, But if we've already got one value in joules, we better just keep all of them in joules, or we're going to get really confused at the end when we start adding these together. So let's go ahead and change this to our 5,000 joules. Keep these all in the same unit. Our next part, after melting, we're going to need to warm the liquid. Warm the liquid water. So that's our next stage, and we're warming it up so that we come back to our Q equals MCAT. Mass of 15 grams. Specific heat now of water is our familiar 4.18 joules per gram degree Celsius. And this time we're going all the way from or melted water, just barely melted, all the way up to the point where it vaporizes. So think about it. That's going all the way from 0 up to the boiling point of water, and we should know the boiling point of water as 100 degrees Celsius. So we've got a full 100 degrees Celsius change in temperature. That's going to give us a Q value for this stage of 6,270 joules. So we're getting there. Our next stage, stage 4 out of 5, we're going to vaporize the liquid or boil the liquid. I prefer the term vaporize, but I also prefer it spelled correctly, but vaporize the liquid. Okay, so once we're into a phase change, we know we're back to using Q equals mA. But the delta H in this case needs to be the vaporization value. Now we look back up at heat of vaporization for water and we see it's 49.8 kilojoules per mole again. So once again, we're going to need to take that 15 grams and convert it to moles like we did for melting. So the 15 grams divided by the molar mass of water, 18.02 grams per mole, is going to give us our moles. And the heat of vaporization we just said was 49.8 kilojoules per mole. So another situation where once we multiply this, we're going to come out with 41.5 kilojoules, but let's please, please, please keep it consistent and go ahead and change that to 41,500 joules for our fourth value. On the last leg of our journey, I guess next to last because we do need to add them up in the end, we are going to be warming the gas. So when we warm the gas, heating it up, we're back to Q equals MCAT. I'm not going to scroll back up to the top, but if you look back up to the top, the specific heat of, oddly enough, the specific heat of the gas is the same as that of the solid, 2.0 joules per gram degrees Celsius. And the temperature change, if we're going from 100 up to 122, that's a 22 degrees Celsius change. So we end up with 660 joules for this value. Our very last step then is to take all of those values and add them together. So we've got 150 joules plus our 5,000 joules. I didn't ever underline that. I like to be consistent at least most of the time. Our 6,270 joules, our 41,500 joules, let's put an addition symbol there instead of comma, and our 660 joules, and I get 53,580 joules. I can report it as 5.36 times 10 to the fourth joules, or I can report it as 53.6 kilojoules. Either way, that is the total amount of heat involved in this process.